If you've been tracking the latest papers on long-context AI, you've probably noticed a quiet but massive shift happening under the hood. We're moving past the era where scaling models just meant throwing more attention heads and parameters at the problem. The bottleneck is no longer just compute, it's the quadratic memory wall of self-attention. And that's exactly why state-space models and architectures like Mamba are suddenly dominating the research conversation. Let's break down why they work, how they bypass the attention bottleneck, and what this means for the next generation of reasoning models. To understand why state-space models are gaining traction, we first need to look at what's limiting transformers. Self-attention computes pairwise relationships between every token in a sequence. That means the computational complexity scales quadratically with sequence length. For a model processing 10,000 tokens, you're looking at 100 million attention computations per layer. On top of that, the key and value matrices have to be cached during autoregressive generation, which rapidly exhausts GPU memory. This isn't just an engineering inconvenience, it's a hard mathematical constraint that forces us to chunk sequences, use sparse attention, or rely on compression techniques that inevitably leak information. State-space models take a completely different approach. Instead of computing global pairwise interactions at every step, they treat the sequence as a continuous dynamical system. In control theory, a state-space model maps an input signal to an output signal through a hidden state that evolves over time. The core equation looks like this. The hidden state is updated by multiplying the previous state by a discretized transition matrix, then adding a scaled input. The output is a linear projection of that hidden state. The advantage is that this operation scales linearly with sequence length, both in compute and memory. You only ever need to store one hidden state vector, regardless of how long the context gets. But early state-space models had a fatal flaw for deep learning. They were inherently sequential. You couldn't train them efficiently on GPUs because each step depended on the previous one. That changed with the introduction of parallelizable discretization techniques. Researchers figured out how to convert the continuous time differential equations into discrete time updates using methods like zero-order hold. Once discretized, you can compute the entire sequence in parallel during training by leveraging convolutional operations. You slide a fixed kernel across the input sequence, and because the kernel is constant after discretization, you get a fast, highly optimized matrix multiplication. Then, during inference, you fall back to the efficient recurrent form. This hybrid approach gives you the best of both worlds, parallel training speed and linear inference scaling. The real breakthrough, though, came with selective scanning. Standard linear models treat all input tokens equally, which means they struggle to preserve critical information while discarding noise. Mamba introduced a mechanism where the transition matrix and input projection become functions of the current input. In practice, this means the model dynamically adjusts how much information to retain or forget at each step, based on the content it sees. It's not a hard-coded forget gate like in an LSTM. It's a learned, input-dependent transformation that lets the model route information selectively. This gives state-space models a form of content-aware memory that rivals attention, but without the quadratic cost. Of course, the research isn't claiming state-space models will completely replace transformers overnight. The field is moving toward hybrid architectures. You'll see models that use attention for local, high-resolution reasoning and state-space layers for long-range context propagation. You'll also see researchers experimenting with higher-order state spaces, multi-scale convolutions, and differentiable integration methods to improve stability and expressiveness. The underlying math is still being refined, and there are open questions around how well these architectures generalize to out-of-distribution reasoning tasks, how to effectively pretrain them on massive corpora, and how to integrate them with reinforcement learning from human feedback. But the trajectory is clear. We're entering an era where architectural efficiency matters as much as parameter count. If you're working with long-context applications, fine-tuning on specialized domains, or deploying models on edge hardware, understanding these linear alternatives isn't just academic, it's practically necessary. The latest papers are already showing that carefully tuned state-space models can match transformer performance on language modeling and reasoning benchmarks while using a fraction of the memory. If you want to dive into the actual math, I highly recommend looking into the original Mamba paper and the follow-up work on parallel state-space layers. The code bases are open, the research is moving fast, and the architectural landscape is shifting in real time. Let me know in the comments which direction you think AI research should take next, and I'll see you in the next one.